Hi, good afternoon. I am David Jedynak. I'm the Chief Technology Officer from Curtiss-Wright, as in we invented the airplane. That was a very long time ago. Curtiss-Wright as in Glenn Curtiss and the Wright brothers. I am the CTO for the Defense Solutions Division of the company. We do a lot with aerospace and defense. So what I want to talk to you about is something that's not really all that exciting usually when we talk about space, because it's something I think a lot of people take for granted. And I should note here quickly, especially since I think she's watching, my wife participated in part of this because she used to work at my company and is focused on operations and manufacturing. So there's one slide in here that's specifically about her concerns about this. Anyways, computing electronics is generally something that people don't think about. I don't see a lot of it. There aren't a lot of papers. But it's important because it's part of the infrastructure of what it is that we need to do. So this is going to be a fire hose. Some of these slides are typically a 4-hour presentation. So I'm going to go quickly, but I'm going to cover what the challenges are, something called OpenVPX, talking about the environmental challenges, something about a capability set baseline, building blocks, reference architecture, metrics, and then some in-situ maintenance, manufacturing issues, and some next steps. So this is going to go quickly, so hold on. So when we look at this particular environment, Mars surface, we have a bunch of challenges here that have to be addressed with regard to computing. When I say computing, I mean networks, displays, storage, all of that makes everything work. So rovers and radios and you name it, whatever, they all have these challenges. So when you look at this, it's very cold, number one. Sand and dust, which we've been talking about, thin atmosphere, high shock and vibe. So in the movement from Earth to Mars or whatnot, high shock and vibration, both in an operational scenario as well as not op. High criticality. So if it does not work, you cannot just call the guy from Dell and have him come over and fix your laptop. That's not going to work that way. Radiation, obviously an issue. It's a harsh usage and maintenance environment. And then the supply chain, like I just said, is very, very long. Although the CubeSat presentation said maybe we could do it in a few days, but that's still not very helpful. So, like I said, I'm going to go quickly, and I'm going to start passing something around. So, solving this is an industry that's been around for a very long time. Go ahead and pass it around. That is a bare version of one of these boards. That is something called 3U OpenVPX. This is out of the aerospace and defense industry. It is of, by, and for the industry. It is a VITA standard. VITA is the organization been around since the 80s. It's actually an anti-national standard. It's used worldwide. For those who understand defense industry, when I say ITAR free, you should understand that that means there's no restrictions with regard to defense use. So key on this here, that module in the upper left-hand corner, that's something called a 3U VPX module that has what's called 2-level maintenance covers. It has wedge locks, that's part of the thermal solution. It has these key blocks, and as I pass this around, you can see in the key blocks, make sure it goes in correctly. The connectors, which are very high speed. I'm not gonna read everything here, but the point is that this is all open standard, and it's all designed to deal with harsh environments. So, one of these will be on a missile, or on a spacecraft, or on a tank, or a fast jet, or you name it, low Earth orbit. We've put these in low Earth orbit. We've used the same part number in low Earth orbit that we've used on big UAVs for the Air Force. And these have been used for other environments as well, so some industrial uses as well. The way it works, you have a module, you have a backplane, you have a chassis. From a thermal management standpoint, this card doesn't show it, the one that's bouncing around. That's just a little example to show some of the size. But the way that it works is we design those modules to move all of the heat from the chips to the edge, to the card edge, where those wedge locks are. It goes in a slot, we clamp it down, you get a thermal interface, and all of the heat on even a 200-watt card like that goes all the way to the card edge, and from there flows into the chassis, at which point the chassis designer gets to do with it as he pleases. So that could be a liquid loop, that could be natural convection, that could be radiative, it could be a cold plate, it could be anything. The point is, there's no moving parts at all. So I design supercomputers, go under wings, that work exactly like this, no problem. Key thing on all this too is those connectors on the front. Those are what's something called MIL standard 38999 connectors. Are very common. You see them also in aerospace and something similar in space already today. Those are designed. They can be used gloved hand, separated at the right distance to be gloved hand. You've got even radiation hardening techniques. I can't dive into those. I don't have enough time. But there's ways that we can make these commercial modules work in radiation environments through some tweaks to the backplane. One of the other things that's critical about this is the backplane itself allows for things like blind mate, coax, and optical. So if you want to do RF cables in, you want to do optical communications, etc., all of that is blind mate, highly rugged. Like I said, again, something like this could go on a launch vehicle, no problem whatsoever. One of the other key things is there's hundreds of thousands of boards like this that have been deployed. That particular board just happens to be one of the very first ones ever designed. That was in 2007. So this is a standard that's been around for a long time and widely adopted across the industry. And many well-defined profiles of the types of modules. So that normally would be like a 4-hour presentation to go through all the details of this. So, this is going to sound simplistic, but when you look at those challenges I threw up, they're very cold. Not a problem. That actually helps us out. It makes it really easy to do our thermal management. Non-op cold in shipping can be a little bit of an issue, but part of the way they're designed will overcome a lot of those issues. Sand and dust, we deal with it all the time. It's out in Afghanistan, Iraq, you name it, wherever. That's not a problem. I hear people talk about it. We've looked at it. It says, what if you pull a module and you put it back in? Are you going to screw up the thermal surfaces, et cetera? You just wipe it off, put it in, it's fine. I've even looked at the way that we test now, and the number of microns on the particles aren't much different than what we're saying is off-world, either Moon or Mars. High criticality, we already do things like FAA, safety cert. So one of those is used to fly the aircraft that you're in, and that's not an issue. There's some sparing and redundancy analyses that have to be done. Designed for 2-level maintenance. So when I say mop gear, that's the stuff that like the soldiers will wear and when bad things happen, and they can do all the maintenance with those things on, with the gloves and whatnot. There is an issue though with in-situ. So on Mars, the depot considerations, fixing, how do you do all that? Radiative cooling, natural convection works really well in the thin atmosphere. So Mars surface is roughly 80,000 feet terrestrial. Okay, that's thin, but it's not zero. There's plenty there that you can still use, even just a gentle like wafting of air. This still does a lot to conduct things away. The specific heats are different, but that's okay. It's pretty straightforward. I've recently designed things with, like a gentle, like a hand waving at 60,000 feet for, 3 kilowatts. No problem. Lots of ruggedization standards and testing, no problems. We do all that. The radiation I talked about a little bit. The sparing analysis will be critical on that. And on the supply chain, again, it's MTBF. That's one of the biggest things we're going to get worried about. And pretty soon you're going to start seeing an Excel sheet that's pretty complicated. So capability set. So I'm going to talk about capability set. What is it that we're trying to do in an outpost or a colony with lots of people? We need things. I'm not going to read all these, but you need communications. You need general purpose computing. You need high performance computing. Maybe special tailored high performance computing to do certain tasks like medicine or radio astronomy. Situational awareness. Frankly, tracking the weather, seeing the dust storm coming in. Tracking the inbound meteors and seeing that they're coming. And so we're talking about like radar systems where you can see the threats coming, perhaps even responding to them. Machine learning systems, which is just kind of a variant of some of these others. Application-specific real-time control systems. The thing that controls the airlock door or the flight of the UAV or the whatever. Those are real-time safety critical type applications. Robotic or remote systems, data storage, HMI, security's in there. I'm not talking really about that here. It's in the paper. But all of these are these sorts of capabilities that we want to have. So how do we go off and do those? So building blocks. So again, fire hose of info here. What I have started with is a set of building blocks that are, this is the set. This is the entire inventory. So there's a single board computer. So basically think of it as a rugged laptop. but it's not. It's a board like the one floating around here. Ethernet switch, all of these are in the same form factor unless I say otherwise. Ethernet switch, so like 100 gigabit Ethernet switch on a blade like that. Flash storage module, graphics processing unit, like a high-end NVIDIA, use it for number crunching or graphics. FPGA modules like high-end Xilinx parts. Server processors like a big Intel Xeon D or a AMD EPYC. Control processors, so something like a Xilinx MP sock, which is really good. It has a FPGA fabric, has a lot of A to D, D to A capabilities. It's running a processor, like an ARM processor. You can use do hard real time in that. And lots of different I/O types. Software-defined radio, like a EDIS National Instruments USERP. So you can do up to 6 gig, real easy, direct RF. Do any waveforms you want. Wideband transceivers. So I'm talking about high-end wideband transceivers where you're going up to 60 gig or something like that, where you can either do narrowband or wideband for either SATCOM, or you can, in fact, we've done that. We've actually sold some of our wideband transceivers that are used for signal intelligence. We have used those as deep space links. P&T modules, so pointing, position, navigation, and timing. So things like a chip-scale atomic clock on there, an IMU, GPS receiver, or other technology for the appropriate environment. And then we get into the power splice, modular power splice. So the thing that converts whatever's on the outside to the voltages internally. Different size chassis, 2-slot, 5-slot, 15-slot, and displays. Also, it's one other comment we have is displays that do things like capacitive multi-touch, but with a glove on, and not a special glove, just a regular glove. Also with the high brightness, you can see it in the sunlight. So one of the keys I want to point out here is there's power, but I want you to see pricing. This is not going to be the technical part. This is the business part. So when you look at these budgetary prices, I want you to understand you're not just going down to Best Buy and buying this stuff. They are more. In some, you'll notice are pretty much one-to-one. At some points, the ruggedization doesn't matter when you're buying an $80,000 FPGA from Xilinx. But you can see there's a multiplier, right? Some of these things are dramatically more expensive. A real-time control box is going to be a lot more than a little Raspberry Pi because of the environment we're building for. But you should understand that. So as you see the numbers, roughly where we're at, call it somewhere like 5x, right? The normal price. But you're buying something that has significantly higher reliability than what you would ever use in your personal life or even in industrial. This is designed to last. Some more metrics, designed to last. So these MTBF numbers are woefully conservative. I took these from like 0-ish C or 10 C operation in a tracked vehicle. That means like a tank zipping along at 60 miles an hour, okay, which is a horrendous vibration environment. So these numbers are already being conservative. So what you can see is, if we talk about a single board computer with 150,000 mean time between failure, that's hours. The failure rate is too low to pronounce. When I talk about MTTR, that's mean time to repair. If it breaks, how long does it take to repair it? Meaning, how long does it take to open the box, pull out the card, put another one in, shut the box, get up and running again? Talk about 1 hour. That's way overkill. Normal ILIDES analysis would say like 5 minutes, maybe 15 minutes, depending on where it's nestled underneath something else. So I've called it an hour because we're on Mars. Anyway, so you look at all that. Let me keep going. So let's talk about a reference architecture. Remember I talked about the capabilities set of what we wanted to do? Okay, so let's go. 30 years, 30 people. So everybody gets their own workstation, and a workstation has a workstation and a network, and there's network nodes. These are big network switches just planted all over the place. Every work area, there's a workstation, right? There's the commons. It's 10 workstations that are, maybe they're acting like Xboxes or whatever. Network infrastructure, this is just the network stuff all over the place, including some RF, which is wideband communication links, as well as the local area networks, wireless networks. When we talk about back-end processing, we're talking about the cloud, if you will, on Mars to have all that back-end stuff going on. And when you look at that, it's got data storage, it has network nodes. Science processing, so maybe it's the specific system that's sitting there doing geology work. It's a little bit different in terms of the processing optimization. Situational awareness, I was talking about like radars and whatnot to see what's coming. And you can see the different pieces I'm putting in it. And I said, okay, how about we have 10 rovers, they're full autonomy. Notice the rover is itself its own little base, right? It's got a ton of these things. You've got a functional high-performance computer for analysis as control systems, autonomy systems. Notice these numbers here are 10. There's 10 rovers, so there's 10 of these, one for each, right? Data storage, autonomy, network nodes, and then UAVs would be similar. They just don't have workstations on board because these are unpiloted. And then I said, you know what, remote sensing units / control units, the things controlling the airlocks, they're just little remote boxes. Let's say there's 1,000 of them for this base of 30 people. So whatever these are little widgets somewhere doing something. So when we look at the per system type, and I'm not going to dig too deep into this, but you can see a workstation is a single board computer, a graphics processing unit, a modular power supply, a 2-slot backplane, and a display. And when you look at that, it rolls up to, 60K. It's 166 watts. That includes the inefficiencies of the power supply. 16.2 kilograms. There's the MTBF. But here's the key thing you need to understand. So operational availability, which says what percentage of the time is it available, is essentially how many failures did you have and how long did they take to get repaired. That's MTTR. You do that math, convert it to versus how long you're using it, and we're at almost 5 nines, right? 99.995. And again, I'm using very conservative numbers. So go across each and every single one of these, you can see where we're at. This is all pretty good in terms of the reliability of all these systems by themselves. Just copy one workstation, one HPC. When I say an HPC, I'm saying let's put 10 Intel current generation Xeon server processors in a box with some other stuff. For the science-focused one, I've got FPGA GPU and x86 number crunching in special ways, right? That's what each one of these things are. And you can see the prices are pretty high, right? That workstation at $60,000, something of equivalent performance would be about $6,000, because this is high performance embedded, this is high performance desktop computing, is the performance level of that. I'm going to go on to the next slide because this gets even more complicated. So if we look at the Outpost, so take my reference design where I said we have this many workstations, this many everything, etc. Take what I just did, throw all that together, and you start looking and you say, in a main living area, all those workstations, that's our operation availability. And there's our price. It's about $2 million for all that stuff. This is on Mars, stuff that works on Mars, not stuff from Best Buy. Okay? So as you go across this, you can see that overall, if we add up all of this stuff, and there's a little fudge in there, this number doesn't add up to those because I put in changing out chassis, not just changing out cards, but having to unbolt the whole chassis and do that as well, those numbers. Looking at a pretty good operational availability. Notice we're at just about an hour a day on average of maintenance for this overall computing architecture using off-the-shelf stuff that you could buy today. We could buy it and send it to Mars right now today. Barely anything we'd have to do different. An hour a day of maintenance for 30 people for 30 years. That's a 30-year estimate. And this is available now today. Again, that's why I say this is not super exciting, but the reason I wanted to talk about it was because I don't really want to see anybody going off and thinking they have to invent something new for this. This is very well proven and very easily done and can be done right away. So I did not include the cost for transit from Earth. I can put that in later. I didn't put in cabling. Those are future things to do. So go down it. So if we look at that, this colony, less than 9 meters cubed worth of gear, less than 12 metric tons of gear, less than 150 kilowatts of gear, just under $90 million. And again, if we do a 5X or 10X, this is an entire facility, science gear, SATCOM, UAV, everything. This is significant. If I were doing that if I was doing it for the DoD, it would cost exactly that much. If I were doing it for just Best Buy and like NASA or something like that, it would still probably be, at least $10 million worth of gear, given some of the gear that's in there is high-end processing gear. MTBF 46 hours, so once every 2 days, something goes down. Worst case, 2 hours we're using to do it. Total failures over a lifetime of 30 years is 6,000 failures. Sounds like a lot, but actually, that's not. It's 5% not available. And you look at what we get. Workstations, high-performance computing, 10 autonomous rovers, 10 UAVs, 1,000 remote sensors, widget, control boxes, radio, SATCOM, wireless, position, navigation, and timing. And oh, by the way, with 2020 hardware, it's over a petaflop of processing. So now you go, okay, but the Colony Challenge was for 1,000. I'm not doing that, but I just figured I'd throw that number in there. So here's that number. And yeah, we're at like about $3 billion now. And this red number is very important. So this is still considering that there's one maintenance guy for all of this out of 1,000 something people. I multiplied by 330 on all these. But you can still look. An IT department would love this. You're servicing 1,000 people and the uptime is more than 95% for every single piece of workstation, for everybody in the company, if you will. Work areas, same thing. The commons, even better. Our network infrastructure, that's pretty good, right? You go across and you start to look and you know where it starts to drop down? Where you have rovers, which are essentially mini bases because they have almost everything on them by themselves. That's on the left columns. And the UAVs, that's actually pretty good. 88% uptime, that's pretty good. You get over to 30,000 something or 33,000, airlock control widgets, and yeah, we're dipping way down. And that's where you can see so we'd be spending one guy would spend 6 hours a day, 8 hours a day, running around fixing things. And then this is where we run into problems. But that's where the analysis has to come in that says we're spending more time per day than there's hours in the day. That's why this number is red, why it's backwards. Because now our operational availability is negative because we're spending more time fixing than we actually have in the day. But this is a scalability thing and then an analysis and a functional thread thing, which I'll get to in a minute. I'm almost done. So, and this is Janet's slide, and this is the stuff she knows really well, so I'm just putting down the topics. So, spares diversity and stocking levels. All those things that break, we have to have spares. So which spares of which, right? I said, here's the set of building blocks. So how do we figure out which ones we need and don't need? And how do you do that without mistakes? You go, oh, well, I ordered a bunch of the wrong thing. I don't need those. I need that other thing. You know how it is at home. You always have like the wrong size screw, right? You're like, I got to go back to the hardware store. You don't want to do that here because you have a very long supply chain. So do you start doing machine learning, predictive, et cetera, which is something that my company already does, predictive as to what's going to go, and hope that it's right and it's not HAL saying it's the A35 unit and it's not really broken? Or is it just a pile of boards? You just keep shipping boards and it's just like a loot box landing on Mars every once in a while. Also, very limited access to specialized repair facilities. It's not like we have a place that can unsolder BGAs and put them on another board. So how do you deal with that? Lack of the local resources. How do you repair and manufacture in situ, right? How do you go take a board, go to an IPC 610 certified soldering guy to go do this fix on a board that got broken? So part of the actions in this would do a level of repair analysis, spares analysis, commonality analysis. How do you keep winnowing this down to a smaller and smaller group? How do you do altered board manufacturing? Are the things we could do to manufacture the boards that makes it easier to fix on Mars than the way that we would do it here on Earth? Are the things you change to make it easier? Are there materials in situ? Can you make heat sinks out of stuff you get from Mars as opposed to something else, or solder or whatnot? And then scavenging analysis. When something breaks, how much can you rip off and put on something else? So next steps on all of this. This is the last slide. Detailed analysis. So these are things that come in if we start talking about, say, like New Worlds Foundation. Rick Tumlinson was here, or New World, Institute, that was here Thursday evening, talking about the space development matrix and whatnot. These are threads of things that you could talk about or go and study. Scalability, repairability analysis, sparing abstraction. Common control cards for diverse control systems. I postulated there's one card that can do many things, and yes, you can, but let's do the analysis of that. The network design, it's way overblown on the numbers I put in there, but I just was using round numbers. HPC system loading and capability analysis, what can I do? And then the cabling infrastructure, that's a whole other issue you have to deal with. And then TRL maturation, and this is what we really get about here, is how do you mature the TRL of these things? Everything I've talked about here is TRL 9 on Earth. Some of it's TRL 9 or 8 in LEO, because it's already been used. We have one particular board from a few years ago that was used in big UAVs for the Air Force, used for radar for the Marine Corps, and used for guidance, navigation, and control for SpaceX's first flight of Dragon. Same part number, right? So high TRL across multiple environments. How do we do that here? I think it would be great if I could do an install at Flashline or at MDRS of this stuff and have this nice, stable, solid network architecture where there's no, RJ45s breaking off. The maintenance, supply, and repair exercises, how do you actually start to say, yeah, I'm in a spacesuit, in a gloved hand, I'm going to pull the module, I'm going to do this, I'm going to put in another one, I'm going to do all those manipulations, because that box is outside on the side of a rover or a UAV, or it's a sensor, or we just lost pressure in our habit, we still have to fix our computer systems. Environmental qualification, radiation environment. We've done radiation stuff. I can't get into it here. It'll be in the paper that's going to be posted online where we talk about something called a smart backplane and the work that we've already done to demonstrate that out. And then the last thing, obviously, to get to an initial operating capability is doing this on Mars surface. I would love to be able to send a small cluster to Mars using this equipment and have it sit there and get used. Anyways, I have like 90 seconds, so any questions? Yes, sir.
First, just want to thank you for this talk. I think the whole world of IT and all the electronics has, as you said, I agree, it's been neglected.
Yes.
And I'd like to be able to follow up with you about this stuff.
Absolutely.
But my question is, all this is designed to mil-spec.
Sure.
Which has been really...
More than that, really.
But does there need, in addition to mil-spec, does there need to be a space spec that will have one set of design criteria for...
Yeah, so the mil specs actually kind of wandered away and disappeared, and we have all these industrial specs now, but I think there are various mil standards, mil standard 810, which basically tells a test tech how to shake something in accordance with a certain environmental profile or how to heat it, and it's all the graphs. If you dwell this long, go up, go down. There are specialized versions of that. So the Army has one that says this is how we do it for the tanks. Use this one, this one, this one, this one, and this one, and these particular procedures, and go do that. Definitely we need those. NASA has done those, but we need those for Mars surface. Here's the specific test procedures to do. Does that answer your question?
Yeah.
Okay.
Well, part of it. Yeah.
Part of it, okay. The other part of it?
Well, you collect all those, the existing mil-spec standards, but some things in space are just different.
Yeah, and we have ones that are beyond that. There's IEEE specs, there's what's called VITA specs. There's a whole number of things that go well beyond what the mil specs were. So that, and you collect them together and you say, here's the Mars standard operational environment spec. Okay, thank you much.
Thank you so much.